Your first task was to complete the residual block class. We know that the residual block doesn't change the shape of any inputs it sees. It just creates a connection between the inputs and outputs using addition. So in this class code, I'm using my helper conv function to define two convolutional layers plus batch normalization. I've explicitly defined a batch norm as true here to remind you that this includes normalization. The residual block takes in a number of inputs to process, and the number of inputs and outputs for each of these convolutional layers is the same. Each of these layers also has a kernel size of 3 and a stride and padding equal to 1. This ensures that the input and output of these layers is going to have the same size in the spatial dimensions x and y. Then, in my forward function, I'm passing my input through these convolutional layers in sequence. First, I'm passing it to my first convolutional layer and applying a ReLU activation function. This gives me my first output. I'm then passing this output to the second convolutional layer and adding it to our original input x. This gives me the ResNet block output that I want. And now I have a complete residual block class that I can use in my generator. Recall that we also have this helper deconv function. And here's my cycle generator code. And I broke this up into 3 steps. First, I define the 3 layers of my encoder portion. This is just a series of 3 strided convolutional and batch norm layers that are increasing in depth. So from an input RGB depth of 3 to 64, then 128, and finally 256. Each of these has a kernel size of 4 and my default parameters for my helper conv function. Next, I'm defining the residual blocks. Here I'm actually going to create a list of blocks based on my passed in parameter nResBlocks. So if that's equal to 6, the default, then I'm going to add 6 residual blocks to my list of residual layers. Recall that our class only took in one input, the number of inputs the block C as input, and incidentally create as output. And this is just the number of outputs from the last convolutional layer, convdim times 4. Then I'm wrapping my list of residual layers in a sequential wrapper and naming them self.resBlocks. Great, then all I have left to define in init is the decoder portion of the generator. This is a series of 3 transpose convolutional layers, and I'm using my helper deconv function here to create these. Just like our conv function, by default these have batch normalization applied to them, and I want that on all but the last transpose convolutional layer. You can also see that these layers are going from very deep to very shallow, eventually a depth of 3 to get the shape of image that we want as output. Moving on to our forward function, I'm calling every one of the layers I've just defined in sequence. And I'm applying a ReLU activation to each of these outputs except the ResNet blocks and the last layer, where I apply a tanh activation function. So this completes my generator class. And in the cells below, I can actually define the generators and discriminators that I want. In this function createModel, I'm instantiating 2 generators, g x to y and g y to x, with a given convolutional dimension and number of res blocks. Then I'm doing the same thing for my 2 discriminators, dx and dy, with a given convdim of 64. In the next few lines, I'm moving all of these models to a GPU device if available. Finally, I'm calling this function and getting my models in the correct order, and it prints out models have been moved to GPU, which I'm running on right now. To check that I've implemented these correctly, I'm going to actually print out the parameters of each of these models, just to make sure they're as I expect. I have my cycle generators with a sequence of convolutional and batch norm layers as the encoder portion, and a long sequence of residual blocks after that. Then this ends with the sequence of transpose convolutional layers and batch norm layers. So you should read over these parameters and check that you have your desired adversarial networks. You should have 2 discriminators and 2 generators. And next, I'll go over how to prepare for training these models.